Hello and welcome to lesson 6.3. Today we're going to look at applying linear functions. What you're going to notice is that many real-world situations can be modeled using linear functions. So we're going to look at how the graph of an equation is going to show the different solutions of an equation. And we also need to understand that not every point may represent a reasonable value. So we'll look at a few examples. So example 1 says, a car dealership has 40 cars in stock. The auto manufacturer will deliver new cars to the dealership by car carrier. Each carrier holds 6 cars. Write a linear function that relates the number of carriers used to the total number of cars at the dealership. Then graph the function that models the situation. So what we have to do first of all is we have to identify what our x and y values are going to be. So x in this case and y, when I read my problem, it tells me that our car dealership already has 40 cars in stock. And then it also tells me that new cars are coming in by a carrier, and each carrier can hold up to 6 cars. We want to relate the number of carriers used to the total number of cars. So I have the number of carriers and the total number of cars. These are the two big things that I'm going to be comparing. Now, the number of carriers, is going to directly affect the number of cars that are brought in. So the dependent variable, or the one that depends on the other, the number of cars is going to depend on the number of carriers. So my dependent is going to be my y value, or this is going to be the number of cars that we have in the parking lot at the dealership, and then x is going to be the number of carriers. So once we've identified that, we can now write an equation. So we can start out by saying that the number of cars in the dealership parking lot is equal to the 40 that we're starting out with, and that's coming from right here. So we're starting out with 40 plus the number of carriers that we have, which we're going to call x. And it looks like we can bring in 6 cars for every carrier. So I'm going to multiply that by 6x. So now, if you notice, I have an equation, which is a linear equation, because this is my b value and this is my mx. So I really have an equation written in slope-intercept form, which tells me it's linear. Now, when I go to graph this, and I realize that this is already done off to the side, but when we graph this, we could create a table of points. So here's my x, here's my y. I know I can't have negative values, so if I just start out at 0, 1, 2, 3, and so on, and I'm just going to plug these values in. So if I plug 0 in to this equation, I have 6 times 0, which is 6, plus my 40, that's going to give me 40 cars. If I plug 1 in for x, I have 6 times 1 plus 40. This will give me 46. If I have 2 cars, I end up with 6 times 2 or 12 plus 40, which would be 52. 6 times 3 is 18 plus 40. That's going to give me 58, and so on. So if we go and we plot these points over here on our graph, you can see that we have 40. Here's our 46, our 52, our 58, and we can continue to go on up. Now, what we have to do is it says graph the function that models the situation. Notice that we have all these individual lines, or dots. We are not going to connect these with a line because when you draw a line, the line says that every point on that line is a solution. And in this case, I can't have a partial carrier. Okay, that's what our x value is. So I can't have a point come in here at, let's say, 1.5 in this spot here. So if I had those 2 points were connected with a line like this, that would mean that any point that occurred along that line would work, and that won't work, or that can't happen in this case because I can't have a partial carrier. So this is going to bring us to the topic of discrete data versus continuous. So discrete data, which we just saw, is data that involves a count of items. Okay, so what that means is it doesn't make sense to have a partial amount, which we just mentioned that it didn't, and it's shown with individual points, like what we just saw in that last slide. Typically, this is the number of people, a set number of objects, etc. Now, when we're looking at continuous data, this is where the numbers between two data values actually make sense to have. So if we can have a half of something or a third of something, then we can actually go ahead and draw a line or show that we have continuous data. Continuous data is shown by connecting the points with a line. So we can have partial temperatures, partial lengths, partial weights, and so on. So for example 2, it says your family's hiking uphill from a campsite, and which is 4,000 feet above sea level. You climb an average of 500 vertical feet each hour. So now, once I see that that rate of each hour, I know that that's probably going to be my x. So x is going to be the number of hours hiked. And my y value then is going to be my altitude, which is really your height above sea level. So when I go to write an equation, I know that my altitude y is going to equal, we're starting out at 4,000 feet. So I'm going to take my 4,000 and then I'm going to add my rate, okay? And my rate is set at 500 feet per hour, or 500x, let's say. So when I come over here to graph this, we know that our x is going to be the number of hours, and our y we set as our altitude in feet. So now when I go to set my scale, I end up with, I can do increments of 1 along my x-axis. So this is going to give me 2 hours, 4 hours, 6 hours, 8, 10. And then if I go along my y-axis, I'm actually going to do a little break and show that we're starting out at 4,000. Then the next one will be 4,500. So I'm just going to put 5 for 5K. Then be 5,500. This would be 6,000, 6,500, 7,000, 7,500, 8,000, and so on. So you can go ahead and create a table of values if you like. So if we do that, I have my x and I have my y. Again, it doesn't make sense to have negative numbers of hours, but I can start out at 0. When I have 0 hours, I have a height of 4,000. After 1 hour, I'm at 4,500. 2 hours will be at 5,000. 3 hours will be 5,500, and so on. So now if I go to plot these points on my graph, we see that at 0 hours, we're at 4,000. At 1 hour, we are at 4,500. At 2 hours, we're at 5,000. And then we're just going to keep going up in increments of 500s, okay, until we get something like this. Now, what you have to ask yourself is, does it make sense? Like, can I travel, instead of going a full hour, could I really go a half an hour? And if I go a half an hour, does it make sense to do half the distance? And because I can travel in half-hour increments or 15-hour or 15-minute increments, it does make sense. So what that means is I can come in here and I can draw or connect these points with a straight line and get something like this. So for example 3, it tells me tickets to a baseball game are $6.50 each. So my x then is going to be the number of tickets. My y is going to be my total cost. So I have an equation that says my total cost is equal to $6.50 times the number of tickets that we sell, which is x. So I'm going to put number of tickets on my x, and my y is going to be my cost. And you can go ahead and set up a table if you like. So if I have my XY table, if I buy 0 tickets, I have $0 spent. If I buy 1, it's $6.50. If I buy 2 tickets, we're at $13. 3 tickets is going to put us up to $19.50. 4 tickets is going to take us up to $26, and so okay, so for my x-axis, I just went and I labeled these as my number of tickets. My y-axis, I went, every line is really equal to 250. And so now what I'm going to do is I'm going to go ahead and plot my points. So I start out at 0, 0. At 1 ticket, I go up to 650, so that's going to be somewhere in here. 2 tickets is going to jump up to 13, so we're going to probably be somewhere up in here. 3 tickets is going to be 1950, which will be just shy of 20. 4 tickets we said is $26, which will be just above. And we'll stop right there. Now I have to ask myself, does it make sense to connect these points? Okay, and I'm going to say no, because X is my number of tickets and I can't sell a half a ticket. So I'm going to leave my graph as just a series of data points. So in example 4, it says students in a 9th grade class drew the following graph to represent how much money would be in a class fund after washing cars at a fundraiser. Part A says, what does the slope and y-intercept of the graph mean for this situation? So our slope, remember, so this would be A, slope is equal to rise over run. So rise comes from my dollar amount, so this is my balance, or my y values, divided by the number of cars washed. So what this is telling me is it's going to give us the actual cost, or the price. So I'll put this as really the price per car that is washed. And if you look at this, you'll see that we should be somewhere kind of around the $3 per car range. Now, it also asks us to interpret the meaning of the y-intercept. Well, my y-intercept, which is right here, looks like it's somewhere in between 20 and 30. So we can imply that it's around $25. Now notice my number of cars washed is at 0, so this $25 is our initial amount of money that we started out with. Now for part B, it says if the graph had the same slope but a y-intercept of 15, what could you conclude about the fundraiser? The only thing this tells us is that we started out with, so we started out with $15 instead of the $25 that we saw in part A. And for part C, it says if the graph had a slope of 5, what could we conclude about the fundraiser? Well, if the slope was 5, that tells us that we're charging $5 for every 1 car, which is our unit rate. Now our last example for today says write a linear function for each graph, state and interpret the slope and the y-intercept in each case. So here it says a caterer charges a flat fee to put it on an event plus a per person cost based on how many guests attend. So what I'm going to do is I'm going to look at this graph, and the first thing I notice is that my y-intercept is a very clear-cut point. It looks like my y-intercept falls on the coordinate point 0, 800. So my y-intercept is really my b value, and that we said was going to be at 800, and it says it's our caterer's charges, so it's $800. So part of my linear equation is y equals mx plus b. So I've already got the b value found. Now what I need to do is I need to find the slope. So my slope, remember, I can find by going y2 minus y1 over x2 minus x1. So I just have to pick 2 points off from this graph. And to be honest with you, I'm going to use that y-intercept of 0, 800. And then I'm going to pick another point, and I'm just going to pick this very end point, which is 6 and 950. And again, you can pick any 2 points. So when I subtract these, I have 950 minus 800 divided by 6 minus 0, which gives me 150 divided by 6, or I have a slope equal to 25. Now again, when I look at my Y values, okay, these are all dollars up on the top. So that tells me that I have $25 per, and then my X values are my number of guests. So this caterer is charging $25 per person. So that is our slope. That's what the slope means. And our y-intercept in this case tells us that regardless of the number of guests that are there, the caterer is going to charge a minimum fee of $800. Please let me know if you have any questions. Otherwise, I'll see you guys in class.